Yes, the surface quality, surface texture is important whenever the surface is to contact with the surface of another component in the structure of an assembly, and there will be a relative displacement between them. Say that one component is moving over the surface of the other component in contact. Then such a case, the surface quality will be important to deal to reduce friction and the wear. Well, the irregularities of a surface over a surface can be controlled in size using geometrical tolerance technique. If the size of the irregularities to control is in the order of millimeter, tenth of 1 millimeter, hundredth of 1 millimeter. And yes, use to control the form of the surface, the irregularities over the surface, flatness tolerance. Flatness may be used, but if the order of magnitude of the irregularities to control is in the order of micrometer, not millimeter but micrometer, 10,000th of 1 millimeter, 1000th of 1 millimeter, 10,000th of 1 millimeter, then we use surface quality definition. Saying surface quality, surface texture, we mean the deviations, irregularities over a surface. These are mainly set by the age of cutting tool. If the surface shaping process is material cutting, or by the abrasive particles of grinding wheel, if the process to finish the surface is grinding process, or to shape the body, shaping process is casting, object is a cast. During the solidification stage, the sand particles over the surface of the template just set a certain pattern over the surface of the object. Depending on the size of the sand particles in the structure of template, we have a certain irregularity over the surface of the object. These are set by the sand particles during the solidification stage. If the surface is a functional surface, I mean saying functional surface over the surface of the object, we have the surface of the other component. These are in contact, there is a mating between them, and one component is to move, display relative to the other component. Then between the surfaces, the irregularities, protrusions will touch to each other whenever one component tends to move with respect to other, or moving with respect to the other, the protrusions, knobs over the surface of the object will be in contact with the knobs of the surface, knobs over the surface of the other component, and there will be a force system at the mating surface applied by one component, knobs of one component, protrusions of one component onto those of the other. When we resolve the forces into their tangential and normally directed components, we see this definition. Tangential component is called friction force. Okay. The resultant of tangential components is the resultant of friction force. Okay. You know, if the surface is dry, the friction force to its maximum value, we have it reaches to its maximum value when the motion displacement is about to start, is proportional with the normal component of the force system. The proportionality constant, you know, is called friction coefficient. Static friction coefficient is used to write that friction force is equal to coefficient times the normal component of the force system when the motion is impending. If the displacement has already started and the component is moving in contact with the other component, then friction coefficient will take a smaller value and it is called kinetic friction coefficient. To be able to decrease the effect of friction, yes, we should decrease if the assembly is a mechanism and one component, thanks to the existence of some facilities, is to do a certain work. For instance, one component is to slide over the other, for shaping a workpiece, or it is the component to move, say to rotate something, whatever it is. One component is to do a work. If the movable part is under the action of friction forces, then the energy input will be partially dissipated by friction forces to the vicinity. How? Friction forces convert the mechanical energy to thermal energy, and that thermal energy is transferred to the ambient. Heat transfer will occur and the energy input partially will be dissipated. To be able to increase the efficiency, mechanical efficiency of mechanism via decreasing the energy dissipation, we need to control the size of irregularities, knobs, protrusions over the surface. In doing this, we use surface quality concept. The main parameter in controlling the surface texture, or using this definition, is the roughness value. When we had a look at a surface pattern, we see, under a certain zoom factor over the surface, we see such irregularities. Mainly these are set by the edge of cutting tool during the cutting process, or irregularities set by the abrasive particles of the grinding wheel during the grinding process, as I said, or if the object is a cast, during the solidification, sand particles of the template will create a certain pattern over the surface of the object. If the surface pattern has been set during the cutting process, material cutting process, depending on the direction of the cutting tool, over the surface we have protrusions and adjacent to the protrusion cavities. The shortest distance between the protrusion over the surface and it is adjacent cavity is called roughness. Over the surface, since the hardness is not uniform and also the cutting tool is oscillating because of the effect of background oscillation, the roughness, value of roughness won't be a specific constant value. Over the surface at a point, roughness may be equal to a certain value, and then well, following place it may be greater or smaller. Since the roughness is not the same over the surface, then need to use average roughness value, average roughness height. It is the say the dominant parameter in controlling the surface quality, surface pattern. The main parameter which is used in controlling the surface quality is roughness value, roughness height. To be able to inform the reader on a technical drawing that the surface quality is in such a characteristic or surface is to be finished for having such a pattern, we use annotation technique, surface quality symbol. Surface finishing symbol is like a check mark. Here in this slide there's an example. Say to show the surface quality symbol on the technical drawing, we use the view where we have the edge of the surface. If the space in the vicinity of the view, in the vicinity of the in the vicinity of the projection of the surface, there is an available empty space, directly bring the surface finishing symbol to its tip into contact with the edge of surface, and then write the necessary numbers and show the lay direction symbol. Now in this slide the numbers are shown in the old format of the standard. ISO already published a document. It is about surface quality and the format of surface texture symbol. In this format, as it is seen in this figure, roughness height, arithmetical average roughness height is written over here. Okay, roughness with cutoff value just under the shoulder, horizontal tail of the surface finishing symbol. Okay, above the shoulder, if necessary, write the waviness height and waviness width, and this part in the vicinity of the symbol is used to show the lay direction symbol. Lay means the direction of the irregularities set by the edge of cutting tool. If the direction of the irregularities with respect to the edge of the surface is in perpendicular direction, we use this symbol. if the lays, the direction of the irregularities over the surface is parallel to the edge of the surface on the view, then we use different symbol, parallelism symbol. Okay, roughness width value, if necessary, written next to lay symbol. Well, since mainly we control the size of waviness using flatness tolerance, seldomly we write those numbers. Well, the valuable numbers to find, to provide, to write are roughness height and roughness width cutoff. While the roughness width cutoff, to its meaning, practically, means it is the length of the path over the surface. Path has been selected to move the probe of the inspection instrument. Well, standard says that multiply roughness width cutoff value by 5 to determine the total length of the path. For measuring the roughness value, roughness height, the probe is to be dragged, is to be moved along a path, the selected path, in this order. The length of the path to move the probe is equal to roughness width cutoff times 5, unless otherwise mentioned. Yes. Standard fully describes the size and shape of surface finishing symbol. Today, the CAD software, to its configuration, can inherently satisfy the format requirements. While the surface finishing symbol, to its shorter leg, to its longer leg, and to its shoulder, is to be in such a size. Inclination 60 degrees, okay. From the tip of the surface finishing symbol to the shoulder, the distance 3 times x is here the font height. Okay. And in this table, you can see in the vicinity of the surface finishing symbol which places are used for providing or for finding which values. Okay. It is the only number written in micrometer in engineering drawing over a certain view. It is the roughness height. Unit of measurement in the first quadrant projection, in accordance with ISO, is micrometer. Roughness height is expressed and it is shown in micrometer. All the other dimensions, while the numbers in the vicinity of the surface finishing symbol and also the dimensions of the features are all shown in millimeter, but only roughness height, yes, is expressed in micrometer. If the quadrant is the third quadrant projection, then the roughness height is written in microinch, and the other numbers, surface cutoff value, roughness width cutoff value, roughness width cutoff value, is written in inch. Waviness width, waviness height, these are also written in inch, but roughness height in microinch. Okay, over a technical drawing on the view, yes, if the space in the vicinity of the edge of surface or the limit of surface is free, empty, then we'll bring the tip of the surface finishing symbol directly into contact with the limit of surface with the edge of surface. If the region is crowded with some other annotations or dimensions, then use a leader line, okay, to reach a more suitable empty space in the vicinity. Okay, well, similarly, similar to geometrical tolerance indication, if the space in the vicinity of the projection of the surface is not available to show surface quality symbol, it is because crowded with some other things, then well, find an extension line. It has been extended from the edge of the surface, and with a leader line indicate the extension and then show the surface quality symbol. Here this indication to say that profile surface, to say that this profile surface. Well, if more than one surface is the surface quality is the same, then yes, write the surface quality, show the surface quality symbol once with the corresponding leader lines. For instance, this indication to say that not only for this surface but the other surface the roughness value is the same. Okay, if for a surface quality has been specified by the designer, and so it is to be shown on the technical drawing. For the other surfaces, we use this format. In the old format, surface quality in accordance with the old version of the standard, it is about surface quality annotation. Well, at the top right corner, within parentheses, we show the surface finishing symbol, and precedingly the surface quality symbol with the selected roughness value for all the other surfaces. This indication to say that except the individually indicated surfaces, for the other surfaces, the roughness side is 6.3 micrometer. Yes. Well, today we have inspection instruments, measurement instruments for measuring the arithmetical roughness side. Okay, roughness value. In general, we say profilometer is a measuring instrument. It is used to measure surface profile, surface texture, mainly roughness value. The profilometer in the technology of the device may be a direct contact profilometer or non-contact profilometer. Contact profilometers are commonly used, but beforehand, instead of for measuring roughness height, since at that time there was no profilometer electronical device, we use master specimens and finger test method. Take a specimen from the box for which surface quality has been determined. Okay, using the nail of your thumb, sense the surface roughness over the surface of master specimen, and then, well, repeat the test over the surface of the workpiece. If you can sense that the roughness order is the same or near, then can say that roughness of the surface is the same. Whatever the roughness order has been mentioned for the master specimen is, then can say that the roughness of the surface of the object is the same. We use finger test. But today we have high-tech inspection instruments. Well, in this photograph, well, this copper colored one is the workpiece, and it is surface quality is to be measured. Roughness value is to be measured. Well, this is the device instrument profilometer, and a profilometer has such a probe. At the tip of the probe we have a tiny little, very little nail. It is called stylus. Okay, as it is seen schematically, shown schematically in this figure, stylus is in contact with the surface of the object. Okay, select the path over the surface and move the stylus over the surface along the path. The displacement of the stylus should be equal to roughness with cutoff value times 5. While the stylus is moved by the mechanism of the profilometer, there is a driving unit within this box. Okay, when the experiment is started, then the probe is dragged in the direction from the point selected, okay, toward the profilometer. The probe is dragged along the path, and the irregularities, the size of irregularities are recorded by the probe. If well, as it is seen from this figure, if the stylus is in contact with a protrusion, then the stylus will be pushed. If it is in contact with the cavity, then it will drop. So the stylus will follow the pattern, follow the surface along the selected path. Well, it will be pushed or dropped. Well, if it is this type of probe, it has a magnet, and the displacement of stylus change the magnetic effect. Magnetic field, in the magnetic field, the magnetic force will be smaller, greater. The current created over here, thanks to the existence of electromagnet, will change. So while changing values of the electrical potential in the magnetic field is calibrated, converted to the size of roughness. In the other type, bimetallic strip is used. Okay, well, depending on the level of stress, the bending of the crystal bimetallic strip, we obtain an electrical potential, and the potential is converted to roughness value, making a calibration test. Yes, stylus is to follow the irregularities along the path, and stylus, when it is in contact with a protrusion, will be raised. If there is no protrusion but a cavity, it will drop. So the displacement between this and that is recorded by the instrument. Okay. Non-contact profilometers use optics. Its working principle is a little bit sophisticated. In this photograph, we have contact type profilometer. Well, today can find a display, LCD display, in the design of profilometers. From the display we can directly see the measured value, average roughness height. Okay, for instance, this is the probe, and there is a stylus over there. Yes, bring the stylus into contact with the surface of the body, and then pushing a run button can sample the irregularities over the surface. Yes. ISO published the document for the first time in 1971. That document is about the format of surface finishing symbol and the numbers to write to show on the technical drawing. Today we use different definitions. Well, find the slide. Roughness height, maximum roughness height, arithmetical average of roughness height, average of 5 regions. Since there are more than one roughness definition, well, it is a good practice to precede the roughness height with such a standard text. If the roughness value is the arithmetical average of roughness height, then the number is preceded with this code, capital R, lowercase a, RA. If it is the maximum roughness height value along the path, well, the highest point and the lowest point have been detected. The distance between the highest and the lowest point over the surface along the path has been detected. It's called maximum roughness height. Yes, RT. Or along the path, well, can find 5 regions, and for each region find the roughness height and say that average of 5 regions. If it is the case, then the average of 5 regions has been shown in the annotation, then roughness value is to be preceded with this abbreviation RZ. So standard, well, has been up-to-dated in 1974, and then second edition has published in 1978. Well, the old version of the standard, yes, says that the number written over here is the roughness height. We have end codes. Well, in my presentation you can find lecture notes, find the conversion table. Yes, instead of writing roughness value numerically, write a code, end code. Well, the advantage of using end code is that reader can directly see whether it corresponds to which value. There will be no doubt whether the number written over here is the maximum roughness height or average of 5 regions or arithmetical average of roughness height. Either use end codes or it is better actually. No need to refer to a conversion table. Directly precede the roughness value with the necessary symbol. For instance, if it is average roughness height, then say RA. Actually, in the third edition of the standard, it is highlighted. Okay, do not simply write the roughness value, precede it with the abbreviation to say arithmetical average roughness height RA, maximum roughness height RT, 5 regions RZ. Okay, in the new version it is highlighted. Say the roughness value is to be preceded with such an abbreviation. But unfortunately, ISO changed the format in 2001 in the 4th edition of the standard. ISO said that well, the roughness height is written under the shoulder of the finishing symbol. In the old version, this place under the shoulder, the place is to find the roughness with cutoff value. But the new version, the place is used to write, so to see the roughness height value. Well, such a format changing caused to some confusions. In the old format, old version of the standard, yes, show the surface finishing symbol for all surfaces to satisfy, or for the surfaces except individually indicated ones. Yes, we used the upper right corner. In this example, on the technical drawing, there is no individually indicated surface quality symbol. At the top right corner, there is a note, surface finishing symbol. It is to say that for all the surfaces of the object, the surface quality as it is shown over here with the symbol. If there are some specified surfaces to their roughness value, and those have been shown on the technical drawing, then use this format. In the parentheses have the finishing symbol, and precedingly the roughness symbol to say that except the indicated surfaces, for all the other surfaces, roughness value is equal to that much. In the new version of the standard, the up-to-date time is 2002. Well, standard says that the roughness value to satisfy for all the other surfaces is to be shown not at the top corner but bottom right corner, like this one. Not like that, but like this. And this place, it is just under the horizontal tail of the surface finishing symbol, is to use, to show, to find, to write the roughness value. To be able to prevent the confusions, since in the old version of standard, this place was used to show, to write the roughness with cutoff value. But today, it is the place to write, to find roughness height. So to be able to notice the reader that it is not cutoff value but roughness height, yes, preceding symbol today is very valuable. Okay, if there is a number and the number preceded by such an abbreviation, this means it is not roughness cutoff value, but it is roughness. Yes. Another issue, is 16% rule. Well, average roughness value has been shown is valid with 16% rule. What does it mean? Well, the meaning of this expression comes from the measurement stage in practice. We have a surface, okay, to inspect, thereafter to say something on its roughness value. Well, the length of the path to move the probe is very little in size, in the order of few millimeters. Surface is a big surface, and over the surface, well, can find practically almost infinite number of little paths to move the probe of the instrument. Shall we select all of those to say something on the roughness of the surface? No, of course not. Standard says that first have a look at the surface. If over the surface the pattern entirely the similar, the same, with naked eye it is not possible to distinguish changing on the surface quality. If the quality of the surface to its appearance with naked eye is the same entirely, then standard says that at the inspection stage, first randomly select a place over the surface, okay, and over there, along the path, find a path, define a path, and then along the path, move the probe. During such a first measurement, if the measured value is below 70% of the roughness value it has been shown for that surface on the technical drawing, then yes, only one measurement is comply to measure the roughness value. Okay, along only one path, which at the place of the surface selected arbitrarily, randomly over the surface, if the measured value is less than the 70% of the roughness value shown on the technical drawing, then say that surface is in a good quality as it is shown, as it is specified by the designer. But when it is measured, the measured value becomes greater than 70% of the roughness value which has been shown on the technical drawing, then standard says that select over the surface two more regions, okay, and make the measurement along the paths at the selected regions, and then see the value, measured value. Well, totally this means along three paths, make the measurement and determine the roughness value. If all three measured values are below the limit, maximum equal to the indicated roughness value on the technical drawing, then say that surface is good enough to its pattern, to its quality. But if at least one of the measured value is greater than the roughness value shown on technical drawing, then standard says that over the surface take 9 additional specify 9 additional places, and at those selected regions along the paths move the probe and measure the roughness value. Then there will be totally 9 plus 3, 12 paths. Okay, along 12 paths totally there will be measurement. If total of not more than 2 measured values are greater than the limit, this means surface is in a good quality. Well, out of 12 measurement, maximum 2 measured value may be greater than the roughness value which has been shown on technical drawing. It is okay. While the 10 measured value is equal to the roughness value shown on technical drawing or less than, but 2 of them greater. While standard says that okay, it can be tolerated and the surface can be considered as sufficiently smooth, sufficiently good to its quality. Well, this allowance corresponds to 16% of the measured value. So that's why the rule, those things are known as 16% rule. Okay. Well, in this table, yes, we have surface finishing symbol. In the old version of standard, this place is used to show the roughness side. Okay, well, along the shoulder, below the shoulder, write the roughness cutoff value. If the symbol is in this format, then this means, well, the finishing process has not been specified. It may be a plastic deformation process or material cutting process. But if there is such a bar in the symbol, it says that finish the surface via cutting material. Material removal by machining is required. Okay, if the finishing process is material cutting, then yes, some cases it may be necessary to specify the material removal order. Well, the number written over here in this example 3.5 is to say that, well, there should be extra material before the finishing process, okay, and via cutting the material from the starting surface to the finishing surface 3.5 millimeters maximum, well, satisfy the surface quality requirement. As it is illustrated here, yes, initially the surface has such a part to remove. Okay, cutting process has been started and this part has been removed via cutting. The thickness of this layer is called machining allowance, and it is written just using this part of the symbol. Well, this place is the same place to find the machining allowance in the old version and also in the version of today, new version of this standard. It is place is the same. If instead of having the symbol like this or like that, we have a circle, a ball over there, this is to say that do not apply material removing process. It is to say, if there is no roughness value written over here, this means, that symbol means that do not apply any finishing process for that surface. Keep it as existing pattern quality. But if there is a roughness value written over here, it is to say that well, first measure the roughness of the surface. If the roughness is greater than the one written shown over here, then decrease the size of the irregularities. Okay, roughness, decrease the roughness, but not by applying material cutting process, but applying plastic deformation process. Using a press or hammer, flatten the irregularities. That is the meaning of this symbol. Yes. Beforehand, well, how many years ago, there was no profilometer, electronical instrument in industry to use for measuring the roughness value. We use finger test. Yes. In the old format, you apply finger test, use finger test and say something on the quality. If the roughness of the surface is the same to its order with the roughness of the master specimen, and on the master specimen it is written that quality of the surface is 2 triangle, then show the surface with a leader line or bringing it directly in contact with this edge of surface, limit of surface, or its extension. The triangles? 2 triangle, 1 triangle. If the symbol, it is the surface quality symbol, it was the quality symbol beforehand in the old format. This means roughness of surface, it has been shown with 1 triangle, is greater than the other surface, it has been shown with 2 triangles. Okay, 3 triangles means better quality, 2 triangles relative to the first better quality. Okay, if the surface is to be kept to its existing quality, no finishing process is needed, no finishing process is to be applied, then show the surface with a tilde. Well, actually there is no such a symbol, but such an example, but say that over the surface we have a tilde. Well, take a pointer, a pen, and then say that this surface is to be kept to its existing quality. To say that it is the requirement, then have such a tilde, show such a symbol, okay, in the vicinity of the projection of the surface. It is to say that do not do anything, do not apply any finishing process. Today, instead of using tilde to say the same thing, we use this symbol. Okay. Yeah, yes, this is the conversion table. If the roughness value has been shown with encode, then see which encode corresponds to which roughness value. If it is entry, then it corresponds 0.1 micrometer. If it is N11, then this means it is 25 micrometer. And this is also the table to convert the triangles to roughness side. In the old version, old standard, it was valid at the time. There was no profilometer. We used finger test only. Yes, we use triangles. For instance, on a technical drawing like this, the quality symbol is 2 triangles. two triangles means roughness height may be 25 or 50 micrometer. Why triangles corresponds to a range? Because applying finger test, using finger test, cannot specifically say something that roughness is equal to this or that. Can only qualitatively say that roughness is in this range. And you see in the old format, the highest quality corresponds smallest roughness value was shown with 4 triangles. How about the smaller roughness values? Applying finger test, using finger test, impossible, because impossible to sense the roughness value which is smaller than 1.6 micrometer. But today we have very sensitive profilometers. Using the profilometers we can measure not 1.6 as minimum but 0.01 micrometer even. So well, for this part of the table there is no triangle, corresponding triangle, because it was the technology beforehand, finger test, applying finger test, impossible to measure or sense the roughness which is less than this order. Well, an alternative table to make the conversion from encode to micrometer or microinch. Well, this table, this slide, just to find some examples for which application, which roughness height is recommended. Okay. How the average roughness height is defined or calculated? Well, assume that profilometer is over here, started the experiment, and then profilometer moving along the path in contact with the surface. And profilometer will generate, say the stylus will generate, thanks to the existence of the converter, analog converter, digital convert, analog to digital converter, can record the coordinates of the points. Okay, relative to the level of the starting point, well, it is recorded relative to the starting point whether the point at which the measurement has been gathered is at higher location or at lower location. Well, the rising and falling, these are recorded. Say that this is the first point at which the coordinate has been measured, coordinate of the point at which the stylus just generated the signal. And this is the second point, this is the third point, this is the fourth, etc. Well, all the recorded values to their absolute values are written how? Relative to the starting point, relative to the level of the starting point, well, the measured value in the up or in the down direction. These are written and added. At how many points the measurement has been done? Yes, write the number of sampling as the denominator, and then say that numerator, sum of the measured values to their absolute values relative to the starting point, divided by number of measurement. The result is the arithmetical roughness height. What should be the roughness with cutoff value? Well, this table is to answer the question. If the roughness order, roughness side, arithmetical roughness side, for instance, is 0.4, if the finishing process is lapping, then standard says that roughness with cutoff value is to be 0.8 millimeters. Along the path, 0.8 is the roughness cutoff value times 5, okay, 4 millimeters. Along the path, its length is 4 millimeters. Measure the roughness value. But here there is a problem. Well, our purpose is to measure the roughness side. Well, to be able to perform the experiment, we should know the roughness with cutoff value. From the table, select roughness with cutoff value, but it uses the roughness value. We don't know the roughness of the surface yet. How we select the sampling length? That is the question. Well, make a guess. Having a look at the quality of the surface, say something on its quality. Say that roughness is in the order of 0.4 or 0.8. Make such a guess. And then measure the roughness side. If the measured roughness side is close enough or equal to the roughness side at the beginning you made a guess, then it is okay. No need to repeat the experiment. But although in your guess you said that 0.4, but when you measure roughness side, for instance, you found 3.2, and then repeat the experiment. In that case, since it is measured roughness side is in this order, change the sampling length, not 0.8 but say 2.5 is the cutoff value. Using this number, perform the experiment. If the measured value is equal to or close enough to the roughness side at the beginning it has been assumed or guessed, then yes, do not repeat the experiment. Till you find the guessed value as equal to the measured value, repeat the experiment. Well, this part of the slide can find some recommended roughness values. Okay. If it is the surface of the house of a slide bearing, then the recommended roughness side 0.8 micrometer, maximum 1.6 micrometer. If it is the surface of a shaft and to the surface a gear is to fit, then the surface quality of the shaft is to be in this order. Roughness, arithmetical roughness side should be 0.8 to 1.6 micrometer. Okay. There is a gear and the surface of teeth is to be smooth enough, polished, to be able to decrease the effect of friction forces. If the module, it is a parameter, we use this parameter in sizing gears. Later I'm going to talk about it a little bit in detail. Studying the chapter, it is about gears. Well, recommended value, if module is greater than 2.5, roughness, recommended roughness side 1.6. Okay. This slide is about lay seam ball. On the technical drawing, say that roughness seam ball has been shown on front view, and the seam ball, lay seam ball, is this one. It is to say that lay direction parallel to the frontal picture plane. This means it implies that during the material cutting process, cutting tool is to move in the direction parallel to frontal side of the body. Okay, move the cutting tool from left to right or right to left. But if the lay symbol is perpendicularity like this, then it is to say that cut the material moving the cutting tool, okay, in the direction which is perpendicular to the frontal picture plane. Why frontal picture plane? Because surface finishing symbol has been shown on the front view. Okay. If the lay symbol is cross X, then this means cut the material for finishing the surface, for setting its quality, not parallel to frontal side, not parallel to profile side, but in the diagonal direction. This direction cut and change the direction, that direction as well. Okay. If the symbol is P, if the symbol is M, then well, there is no specified cutting direction. In any direction, surface may be cut. If the lay symbol is C, then this means cut the material at the finishing stage along circular paths. Yes. Yes, the surface pattern is set by the edge of cutting tool. Here, this is the cutting tool and this is the workpiece, and the edge of cutting tool you see is just applying the cutting force, and chip is being removed. Well, here this slide to remind you on the difference between shaper and planer. In shaping process, yes, we use crank shaper. It is the commonly used cutting machine. Well, table of the machine is shifted, okay, to set the cutting tool to the new positioning to cut the material. Okay, table moves in this direction or opposite direction. Okay, cutting tool only moves along the path ahead, and it is called back. But in this principle of planning machine, planning process, while workpiece is stationary in this direction, it is not moved. Cutting tool just stationary. Okay, table moves in this direction. Okay, workpiece is displaced against the edge of cutting tool. But in shaping process, cutting tool moves over the surface. But in planning process, cutting tool stationary, workpiece is moved toward the cutting tool. This bar chart is to see applying which finishing process we can have the roughness value as equal to what? Which roughness side can be obtained, can be set, applying which process. For instance, if the process is, for instance, grinding process, yes, this is the corresponding bar. Well, the darker part, blackened part of the bar, to say that under normal conditions, average application, if we normally apply grinding process, can expect to find the quality of the surface, roughness of the surface in this range maximum equal to 1.6. Okay, minimum 0.1 micrometer. Okay. Actually, if the roughness side is the one to set for the surface is in this range, well, even we may not indicate the roughness symbol for that surface over technical drawing, because under normal conditions, average application, it is possible to set the roughness in this order. But whenever the roughness to set applying grinding process is in this order, then yes, since it is not average application but less frequent application, surface roughness symbol must be shown. Opposite case, surface should be in this roughness order, a poor quality, not average application but less frequent application. Either the roughness is to be the one smaller than the average application result, or a poor quality greater roughness than the one it is obtained under normal conditions applying grinding process. This case or that case, well, the roughness symbol must be shown on technical drawing. And also, well, drawing such a line and then say it starts from here, well, it corresponds to 3.2 micrometer. Well, can see if this line just crossing the average application part of bar charts, can say that normally applying, for instance, sewing process, planing shaping process, okay, drilling process can have such a roughness value. Under normal conditions, applying which process can set the roughness to 3.2? That is the question. Follow this path and then see this line crossing the say the average application part of which bar, and that bar corresponds to which process. For instance, this is crossing planing shaping, the bar of planing shaping process to it is average application portion. This means while applying planing or shaping process, we can have the surface roughness in this order 3.2. But applying planing process cannot, under normal conditions, cannot have the roughness value, for instance, 0.1 micrometer. It is impossible. The surface is a cylindrical surface, okay? Cylindrical surface. Although the surface to finish is cylindrical surface, you selected planing process. It is wrong. Planing process, shaping process is the process to create flat surfaces. Cannot create cylindrical surface. For cylindrical surface, the finishing process may be grinding process, rolling process, or if it is a hole, drilling process. Yes. Planing shaping, lapping, turning. Yes, turning. Using lathe machine, yes, can apply turning process. Using lathe machine, applying turning process, we can cut material for having a cylindrical surface. Applying turning process, which roughness value can be obtained, can be set. This darker part of the bar is to use for answering the question. Applying turning process under normal conditions, saying normal condition, I mean the cutting machine is not a brand new one. Technician is not a high quality technician. Okay, so the things are average. The cutting tool is not so brand new. Technician is a normal, ordinary technician. So apply the process, turning process. Can expect that roughness value will be minimum 6.3, say maximum 6.3, minimum from here the darker part corresponds to this number, 0.4 micrometer. Okay, this bar chart is valuable to see such things, to find the answer of such questions. Which process is recommended under normal conditions to apply for having which roughness value? Well, we refer to this table and then try to answer. And the last part is about knurling. Knurling is the surface pattern to set, not say at the surface cutting process, surface forming process, but it is the process specifically created for having a specifically created pattern. Knurling is a process of impressing diamond shape or straight indentations on the surface of work. The purpose of knurling are to improve the appearance of the work and to provide a better grip. Yes, most of the cases, if it is the handle part, okay, to rotate, to hold and rotate, then to be able to increase the effect of friction, to have a better gripping, well, yes, create a certain pattern over the surface. Using the knurling tool, applying the necessary deformation force, we create such a pattern over the surface. Existence of this roughness over the surface specifically set by the knurl tool is called knurl. Okay, it is the handle part of the spindle of an adjuster, for instance. Yes, thanks to the existence of such a pattern, we can much more easily grip and rotate. Okay, if there is a knurl over the surface, then yes, on the technical drawing, well, with a leader line, indicate the knurled part and then write the pitch value and the type of the knurl, straight knurl, diamond knurl, pitch. Pitch is the shortest distance between protrusion and adjacent protrusion distance. That distance corresponds to the distance between the indentations of protrusions of the say knurling wheel. If distance from here to there is equal to such a millimeters, then using this wheel, when we created the indentations applying the deformation force, well, the corresponding pattern will use the, say, will have the same distance. Whatever the pitch value, distance from here to there in the rim of the knurling tool is, then the distance between the protrusions created by the knurling tool will be in the same order. So since the pitch of the knurling wheels are standard, for straight knurl these are the values 0.5 millimeters, maximum 2 millimeters, diamond tool 0.6 to maximum 2 millimeters. Well, which knurling tool is to be used in which size? It is written along the shoulder of the leader line. Okay. Yes. And then the last part is to say that there is a relationship between the displacement speed of cutting tool, okay, and the roughness value. Yes. F, lowercase f, is the lead of the cutting tool. Okay. Lead of the cutting tool. RA is the average roughness height, and F is the lead of the cutting tool for one turn. Okay, say that machine is turning machine, process is turning process. Well, this is the workpiece and it is rotated by the chuck or the lathe machine. While it is rotating, while cutting tool is moved in this direction, and well, we have the cutting force over here to overcome the atomic bonding forces. We're cutting the material. For one turn of the workpiece, what is the displacement of cutting tool? For one turn, the displacement of cutting tool is F. Okay, square of F divided by a coefficient times the rounding radius of the edge of the cutting tool. Okay, well, it looks like subtraction, but it is well, quite misleading, I agree. It is to say that if roughness value RZ average of 5 regions is greater than 25 micrometer, then use this number at the denominator. If the roughness is less than 16, then use this number. Such a number times the rounding radius of the tip of the cutting tool is the term to write at the denominator. Numerator, we have the square of the lead, F. Okay, this is an empirical formula. Well, the result of this division, this calculation gives us approximately the average roughness height. Okay, last slide, you can see two pictorial figures, two different objects, and then, well, considering the written text here, show the surface roughness symbol on technical drawing. Okay, well, after studying on my lecture notes, then the following part will be, of course, CAD application part. The second video is just to answer the question in Inventor how the surface quality symbols can be added on a technical drawing. Which button is to be clicked for having surface quality symbol in the end? Answer this question in the next video. Thank you.